All right, let's get started. Thank you guys for having me here. Thank you for Epic Labs for hosting, and thank you for the Swarm team for putting on the party. My name is Eric Tang, and I'm from the Livepeer team. And presenting with me is Ignacio from the Epic Labs team, and he's going to show off some awesome research results that we've been collaborating on. So the topic of today's talk is verification of decentralized video transcoding. And this is one of the key components in the Livepeer network. So what I want to cover today is to give you a brief overview of what the Livepeer network is, kind of introduce that to people who are not already familiar. And then I'm going to introduce the current phase that we're in, which is called Streamflow. And this basically allows the Livepeer network to scale to be able to power a major internet video application, something like a YouTube or like a Twitch. And then I will, and Ignacio is going to give you a demo on the research results that we've been collaborating on, and I will talk a little bit about what's coming next. Okay, so Livepeer, if you're not familiar, is a decentralized video infrastructure. And what that means is that it's a developer tool that allows people to build video applications. Currently, the way video works on the internet on a very high level is that for a broadcaster, if you're a broadcaster, you're on the very end with the camera. You either have a live stream or maybe you have a video file itself. You upload this video into a cloud-hosted media server, right? A media server, kind of similar to a web server which hosts web content, a media server hosts video content, right? So you're able to upload the video onto the media server, and the media server kind of serves that video to the internet. But the media server also does a few things that are really crucial. One is that it transcodes the video into many bit rates and many different codecs, and that's why we're all able to watch the same video from around the world. Whether you're on a cell phone connection or you're sitting home with a HD TV with a high-speed internet, right? So even though we feel like we're watching the same video, we're actually watching very different versions of that video, and that's all due to the transcoding. And this is a very key piece of how video can work on the internet in the first place. And the media server also does a few things. It does applies DRM. It can store the video, and it can also do ad insertion, do subtitles, and how about these features, right? And it also serves that video to a content delivery network that then replicates that around the world and serving that to the end user devices. So what we want to do in Web3 and the decentralized world is to replace all of the cloud-hosted parts and put that into a decentralized network. Why do we want to do this? It's because the cloud-hosted infrastructures are owned by large corporate enterprises. And right now there's kind of a monopoly in who is providing these infrastructures. And as a result, there's a lot of perverse incentive in this whole scheme. Right? People paying contracts to these large enterprises that then provide the infrastructure at an artificially low, high cost. So what we want to do is to have this open, decentralized network that has all the features that we can have from this cloud-hosted services. But it's not owned by anyone, right? This is just common infrastructure. Imagine how the internet was invented in the first place. No one really owns the internet. It's just out there. But the decentralized network itself can figure out how to incentivize the participation and getting people to contribute their hardware, getting people to contribute their resources to create this network. So, and the first step to do this is to create a transcoding network, which is what Livepeer is currently working on. Previously I mentioned the importance of video transcoding. And the way this works currently in the Livepeer network is very simple, right? If you're an application or you're a broadcaster of video, you can send that video into the Livepeer network, which consists a bunch of transcoders. And these transcoders, we call them video miners, then do the transcoding work, and they send the results back to the applications. And the network also uses Ethereum to do the settlement and provides security to this operation, so that even though you're working with a decentralized network and you don't know who is providing the computation, you can trust that as long as they are participating in the Livepeer network, the results that they provide will be the result that you asked for. So how does that actually work? We use staking. And staking has many different meanings. Here we use that in the sense that the service providers have something on the line, right? They have something to lose. So if we look a little closer, here are a bunch of the nodes that are active on the network, and each of the nodes share a percentage of their rewards to the people who stake towards them. So imagine if you are a Livepeer token holder, you can stake your tokens towards one of these nodes, and in exchange, the nodes will share a percent of their profits to you. But at the same time, you're also taking on a risk, because if the nodes do something wrong, they will be slashed, and your stake will also be slashed in that process. So you really have to make sure that you're staking towards someone who's honest and someone who can provide the right work. And on the high level, the slashing mechanism works like this. You have the transcoder. The transcoder is giving you the results back like before, right? And the transcoder is creating a cryptographic signature with every transcoded result that comes back, which means now, as the broadcaster, you have the evidence to challenge somebody. And the challenge simply means, I'm gonna ask a judge to decide whether this computation has been done correctly. And the way you issue a challenge is by issuing a transaction to the Livepeer smart contract that runs in the Ethereum network, and believe that the smart contract can serve as an oracle and give you the right answer, right? So this is all good. So why do we need to work on Streamflow, and why do we need to scale this network in the first place, right? Livepeer has been running for about a year, and there's been hundreds of events that have been streamed on this network. So for example, last year, most of the technical tracks at DevCon at Ethereum were streamed on Livepeer. Right? But clearly there are some problems. The reason we want to scale this network is because the majority of the traffic on the internet is video traffic, right? So we're on pace to have over 80% of all the traffic on the internet being video content. And most of that content needs to be transcoded, right? So if we want to build a decentralized network that no one owns and that can serve as a commons for everybody who uses the internet, we gotta figure out a way to make that actually serve all that content and to process all that content. And that's a pretty high order, right? So when we've been working on this for over a year, ever since we deployed the Livepeer protocol on the mainnet as a beta, right? And we've been learning from the deployment, and we've been working on a lot of the research and implementation based on those learnings. So there are a few things that we did here. But one of the things that I want to point out is that the reason this can scale is because we're able to do everything off chain. So we've changed the workflow so that the entire video workflow is now off the Ethereum blockchain and no longer limited by the transaction throughput and the cost of using the chain. So the only thing that requires the Ethereum blockchain now is the initial setup of setting up the node in the first place, and the settlement that happens asynchronously instead of in this video workflow. And that's what kind of enables us to scale this to handle hundreds of thousands of concurrent streams. And another really important thing here is that we are enabling GPU processing. Now, GPU processing is a really it's a scaling factor in the cryptocurrency world, right? Because we all know there are cryptocurrency mining farms out there, and a lot of mining farms run GPUs, right? But so if we look at the architecture of an actual GPU, we realize that there are some processing units on the GPU, but also there are chips on the GPU that are created only for encoding and decoding video, and they can't do anything else. So all of the billions of dollars of GPUs that are deployed out there mining cryptocurrency have these video encoding and decoding chips sitting in the farms and not doing anything. And what we have done is benchmarking against these GPUs and running the cryptocurrency mining operation in parallel with the video processing operation, and showing that you can actually run both at the same time. You just expense a little more electricity, but the amount of profit that you can get is tremendous. Each GPU in the cryptocurrency mining farm makes about, on average, 75 cents per day. But if you apply the same pricing that Amazon charges, for example, for video transcoding, you will see that each GPU can do 2 to 3 streams in parallel. And Amazon charges $3 per hour per stream to transcode. So what that comes out, if you utilize the GPU fully, is $144 a day, which is hundreds of times more than you can make in a GPU in GPU mining. And we expect that this drastic difference in pricing will drive a lot of supply onto this network, and also drastically lower the cost of transcoding, which makes this network very, very attractive, not only to decentralized applications, but also to any traditional video applications. And of course, one of the things that comes with GPU mining is, and GPU-based transcoding, is the non-determinism of this operation. And what that means is, if I put the same video segment into the GPU, I will get different results back each time, right? And this is based on, even though the picture looks the same to the human eye, and this is because the floating point calculation that happens on the GPU. So we've been thinking about, okay, if the computation itself is non-deterministic, how can we actually verify the work has been done correctly? Especially in this decentralized world, where somebody needs to trust some random computer on the network to do the work correctly. And this is one of the things that we've been working on with Epic Labs, and Ignacio is going to come and tell you a little bit about that.
All right. So here at Epic Labs, we have been collaborating with Livepeer in order to check that the videos that the job has been done. These nodes are doing all this work, but there has been to be some way to verify this work. So we propose this, which I think it's a very interesting workflow, in which we work on feature engineering. We were at the start, we're avoiding working with the frames of the videos. We're developing our own features, and then we fit these features to two kind of models that we'll talk about them later. And then we're doing incremental releases. And while we do this, we're creating articles, and we're open sourcing everything. Okay. So on the side of feature engineering, we, as I said previously, we're avoiding working with images just to make this previous workflow that is iterative faster. We have been using some known metrics from computing similarity between images, such as a structural similarity index or mean square error. And then we're using features that are known, such as comparing the histograms of the images in order to check that if the video has been, for example, grayscale, or there has been some vignetting effect. And then we're computing, we're going to other domains, such as the frequency domain with the discrete cosine transform, just all these computations on the images. And then we're also doing edge detection, so this can help detecting, for example, watermarks. And then we're generating time series. We're doing this frame by frame in each of the original asset and on the transcoded video. So we're doing this frame by frame, so we end up with a time series. Right now we're averaging the time series, so we have less data, but on time we'll end up working with the whole time series. So this is just an example of one of the features and what we're actually doing to the images. This is an example in which we compute the edges on an image, and then we subtract at the same time from the original asset and to the transcoded asset. So we can see that if the video, for example, doesn't have a watermark, the difference should be almost zero. There is always going to be some artifacts on the image, but the difference should be almost zero. But if there is a watermark, and now we compute, yeah, we use a Livepeer watermark. That'll be funny if one of the nodes use that. But so the difference should have almost energy zero, that there should be any pixels activated. But if there's, for example, a watermark, it wouldn't be. So this is just an example of the computations that we are doing to the images. On the modeling side, we have, in the previous scheme, we have it split in two parts. We call it supervised learning and unsupervised learning. But basically, on one side, we have labeled data, and on the other one, we don't have labeled data. On the supervised learning side, we use for training assets that have been properly transcoded, but we also use some attacks that we have simulated and that might be on the network, such as grayscaling a video or vignetting, downsampling the colors, even just a black video or a video that is not from the original source. Many attacks, and this goes in the training. On the unsupervised learning side, we don't use that. The training set is just videos that has been well transcoded. So of course, on the supervised learning, we have labels. We have good videos and attacks, and on the supervised and on the unsupervised, we don't have that. We just have videos that have been well collected. So the good thing about the unsupervised is that it's attack agnostic, because there is no bias towards any attack. Of course, the overall accuracy is, at least for the results that we have been achieving, it is better for the supervised learning, but it is biased by the attacks that we have trained. And then, of course, on the unsupervised learning, the accuracy is a little bit lower, but it is not dependent on the kind of attack. We are using some machine learning models. As I said, we're saving the work with images, so deep learning will probably come later. Right now we are using classic algorithms, extreme X boosting, support vector machines, random forest on the supervised learning part. And then on the unsupervised learning part, we're using one class support vector machines, isolation forest, and small autoencoders, so let's not call that yet deep learning. So as I said, everything is open source. We have a GitHub repo where we have created a YouTube scrapper, which takes the videos from a very known YouTube dataset, which is YouTube 8 million. It has 8 million YouTube videos. So we take those URLs, we create the URLs, and with an API, we download them. We have Article 1 and Article 2 talking about the features that we just said. Article 3 is releasing with more features, and eventually, since we have finished the first cycle, we'll have a fourth article talking about the predictions that we have been doing and the models that we have been using. Okay, so let's go for the demo. We have prepared a small demo of the CLI that we have been working on. In this demo, basically, I have an original asset, which is this video. Okay, it's downloaded from YouTube, and then I have a video with a different resolution with a watermark. On the top left, we can see the Livepeer watermark. I have placed a different video, which is this one. It's not related to the source, so we should be able to detect this. And many more. I have done some vignetting, some low bitrate. So right now, let's use the CLI. This is from the GitHub repo. Okay, so I'm just gonna start the Docker and build the image. And right now, I'm gonna call this command, which basically is calling the script. It's giving the original asset and all the possible renditions that we have in this directory. And we're downloading the model from GitHub. Okay, the model is open source. So what I'm gonna do is I'm gonna download the model and then compute the metrics, all the features that we've been talking before, and then we're gonna compute inference. Okay, so this will take 5 seconds. So right now we're downloading the model. Right now we're capturing the frames and computing the features, and we have made our prediction. Okay, so it took 5.5 seconds in computing the features of 6 videos, of which 99% of the time is the feature computing, and then 2 milliseconds to compute the inference with the models. Okay, so the original asset is that one, and we can see that it has actually detected the watermark video. There is an asset with 360 resolution that is legit. There is no attacks on them, and then we have detected the low bitrate, the vignette, and the attack, which is a completely different video. So this is the demo that was ready, and that's basically it. Let's jump back to the presentation.
All right, thank you, Ignacio. As you can see, now we have this interesting classifier that can basically tell us whether a video transcoding job has been done correctly or has been done by a malicious actor in the network. So the next question is, how can we use it? So first of all, we are soon releasing a Streamflow testnet where everyone can try this. But also, this type of classification workflow kind of changes how the protocol works in the challenge step, right? So before I talked about, you might remember this picture where on the bottom right we have something called TrueBit, which is a project that's a decentralized computation verification mechanism, and of course TrueBit only works on deterministic computation, right? So when we have a undeterministic computation, we use a classifier, and this classifier we have a few different ways to use this, right? One is we have to make sure the classifier is trained on a public data set, and this data set needs to be transparent to anyone who's participating in this network, right? So by participating in the Livepeer network, you are saying that I consent to be monitored by the classification model that's trained by this public data set, and this data set is available to anyone, and anyone can use the same algorithm to recreate that model, right? And another thing is, even on the execution of the classification algorithm, if we want to truly decentralize it, we might have to run it on trusted hardware. But that's totally fine. Even though trusted hardware is a little slow, we can see that the actual classification step only took like a few milliseconds. So that would work. And also another interesting approach here is that the transcoders themselves, when they're doing the transcoding job, can actually also be producing these metrics that will be used as parameters to the classification algorithm, and as a result, basically saving time for calculating that for calculating those parameters. And we're starting to work on prototypes that incorporates this metrics calculation into the transcoding step. And this is actually something that can create a lot of value, not only in Livepeer, but also in other video usages as well. Just the fact that when you are doing video processing, you're actually returning the metrics that come with the process. And something else that we have to deal with, of course, is false negatives, right? Any kind of machine learning algorithm has false negatives. And what that means is, even though as a worker, I've done the work correctly, the algorithm has wrongly said that I didn't do the work correctly. So what can we do to deal with that? One way to deal with this is to just run this algorithm. The worker themselves can run this algorithm on every single piece of work that they do, right? So they will know that whether the algorithm has been incorrect in determining if his work is correct. And if that's the case, as a worker, I can simply just say, in those low chances where the algorithm is incorrect, I just won't sign the result that I give back to people, right? And instead, I just say, hey, I'll give you a freebie. Let's continue to work together, but But just don't, I won't give you the evidence so you can punish me for this thing that the algorithm is making mistakes on instead of my own work. Another way to do this would be to have the protocol to keep score. And what that means is, let's imagine we have a 1% false positive rate, false negative rate. So we can, what we can say is, based on the, we can set a threshold, and let's say for every 100 segment that this worker processes, we want to have no more than, let's say, 3 segments that are reported to be wrong, right? So we set some threshold there. And this is made possible because of the probabilistic micropayment scheme that we worked on. I didn't go into that, but the payments, one of the side effects of the payment scheme is that it gives us information about how much work a particular worker has done through the amount that they're getting paid. Another interesting direction is this idea of multi-level slashing, which means the work can be checked in different ways, right? So for example, if I replaced the video with a complete black screen, that could be a different type of punishment than I created some result, but the resolution is low, right? So all these things can be categorized differently, and the verification operation of those of those checks are also different, and it comes with different cost for the network. Therefore, we can punish people by different amounts if they fail certain tests. So another thing that we worked on is integration with Swarm, which uses the Swarm feeds feature that Javier built. Where's Javier? He just left. That Javier has built. I actually recorded a YouTube video and published it. So if you just go on there and search for Livepeer Swarm integration, you'll be able to find it and watch it. And the idea here is that we want to create a really smooth broadcasting experience on Swarm today, right? So earlier we talked about Swarm's long-term vision. When we talked about the current state of Swarm, right? Which is we have this decentralized system, but the system is not incentivized. It's a peer-to-peer network, non-incentivized peer-to-peer network. And what comes with that is the lack of guarantee in terms of bandwidth, right? So we have no idea what's the speed of the connection between all the nodes in this network. And what that means is we'll not be able to guarantee the delivery of something like a broadcast, because the video segments and the video streams are pretty big, right? But what we can actually do is to deliver only the video manifest through the Swarm network, because these manifest files are very small, and all it contains is the information about where to find the video segments, but not the video segments themselves. So if we just store the video segments in a traditional in a traditional content delivery network or something like S3, those networks can guarantee the bandwidth of delivering those specific video chunks, but without the manifest, you cannot watch the video. So the combination of these things is a video broadcasting experience in a peer-to-peer network that's currently just works, which is kind of exciting. And something that can be built on top of this is an ENS integration, which means you can actually use an ENS name to represent a video stream. So instead of having to require a manifest or something, you can have a human readable name, say like, swarmsummit.eth. And if you go there, you'll be able to watch the video stream, which is kind of exciting. So that is all that I have. I think we're a little bit over time, but thank you for being here, and I'll be here all day if you want to ask questions.
Thanks to Ra too.
Yeah. Oh, thanks Ra for doing a lot of the work as well.